Welcome to The Explainer. So today we're diving into how a super simple everyday physics concept is actually harnessed to manufacture some of the most complex, heavy-duty industrial items in our modern world. It's this fantastic journey from invisible forces all the way to massive physical manufacturing, and honestly, I'm super excited to guide you through it. Let's get into it.
Well, let's kick things off with a bit of an engineering mystery. Think about this for a second. How exactly do you create a perfectly hollow, highly durable metal cylinder? Usually in casting, you'd need an inner mold, or a core, to shape that hollow center. But here's the catch, and it's a big one. Those inner molds are constantly breaking down. They shift, they crack under the sheer intense heat and pressure of thousands of pounds of molten metal. It is a massive headache for engineers. So how do we get around it?
All right, Section 1, the power of the spin. Let's understand the physics.
What we're looking at here really nails the foundational concept we're working with today, centrifugal force. It's exactly like swinging a ball on a string. As you rotate the center, the rapid spin forces the mass of that ball outward along a path of inertia. The ball desperately wants to fly off in a straight line, right? But the string pulls it into a circle, and that creates a really strong outward push. We've all felt this exact thing on a playground merry-go-round. Keep that specific physical behavior tucked in your mind, because it is literally the secret ingredient to solving our engineering mystery.
Moving on to Section 2, centrifugal casting. Let's break down the process.
So the brilliant part here is that we can take those exact same inertial forces we just talked about and use them to distribute molten metal. The process is ingeniously simple. Step 1, we grab a mold, and we spin it. Spin it unbelievably fast around its central axis. Step 2, while it's spinning like crazy, we pour glowing liquid metal directly into it. And Step 3, instead of gravity just pulling the metal down into a sad puddle at the bottom, that centrifugal force violently flings the molten metal against the inner walls of the mold. This applies a massive, continuous outward pressure as the metal cools and solidifies.
Section 3, True Centrifugal Casting Techniques.
I absolutely love the contrast here. On one side, you've got this super precise engineering diagram showing exactly how the mold rests on the drive rollers. But then, right next to it, you see the intense, real-world application on the factory floor. It's a massive, glowing, red-hot metal cylinder being formed in real time. It perfectly bridges the gap between the clean, quiet lines of a blueprint and the raw, intense heat of actual industrial manufacturing.
And let's talk specs for a minute, because pulling this off is no joke. To manufacture heavy-duty items, and we're talking serious infrastructure here, massive pipes, gun barrels, engine cylinder liners, even the street lampposts in your neighborhood, engineers use molds made of incredibly tough stuff: steel, iron, graphite. They rotate these molds usually on a horizontal axis at just staggering speeds, anywhere from 300 to a massive 3,000 revolutions per minute. That is a tremendous amount of kinetic energy being transferred to that molten metal just to force it into a perfect cylindrical shape.
Okay, Section 4, the hidden benefits, or as I like to call it, a very happy accident.
Turns out, spinning liquid metal at these insane speeds creates this wild, super beneficial quirk of physics. It's literally like a salad spinner forcing heavy water out of lighter lettuce leaves. The intense spin automatically categorizes the molten materials by density. The heavier, pure metal is forcefully pushed all the way to the outer edges to form the strong exterior of the part. Meanwhile, the lighter materials, the slag, the oxides, basically all the impurities you absolutely do not want weakening your final product, they naturally segregate and just kind of float towards the hollow center. And then they can just be machined right out later. It essentially purifies the casting as it forms. How cool is that?
And the perks just keep coming. Because of that relentless outward pressure, the liquid metal forms an absolutely perfect, uniform inner cylinder. Remember that massive headache we talked about at the start? Officially solved. No fragile inner core required whatsoever. Plus, because solidification begins at the cooler outer surface and works its way inward under pressure, the process naturally compensates for metal shrinking. That means fewer extra parts, like risers, are needed to feed more metal in. Engineers can even use this technique to pour two different metals back to back. So you end up with bimetal castings, like a pipe with a super hard, wear-resistant outer layer but a flexible, ductile inner layer. It is incredibly versatile.
Which brings us to Section 5, intricate shapes, centrifuging casting.
Now, not everything we manufacture is a giant lamppost, right? Sometimes we need really delicate, ultra-precise metal parts. Enter a variation called centrifuging.
This utilizes relatively lower rotational speeds to help force molten metal into what we call multiple product investment casting trees. Actually, think of it like this. Instead of making one big hollow tube, the spin pushes the metal outwards into dozens of tiny, highly detailed molds branching off a center stalk. It just goes to show that this outward force works beautifully for ensuring sound castings with thin walls and intricate shapes, just as well as it does for massive industrial cylinders.
Zooming back out to the massive scale for a second, just look at the raw energy in this scene from the foundry floor. Seeing the intense heat, the glowing metal, and the heavy machinery, it really gives you a deep appreciation for what manufacturing actually entails. We've taken a fundamental law of physics, literally the exact same force that smashes you against the car door when taking a sharp turn, and we've totally tamed it. We engineered it to build the hidden backbone of our civilization, from the engines in our cars right down to the pipes carrying our water.
And that brings us to our final takeaway. The structures around us aren't always just poured into a static box. A lot of them are born from intense, violent rotation. It leaves us with a pretty fascinating perspective to take away from this explainer today. Next time you walk past a seamless steel lamppost on your street, or you look at a heavy-duty engine, I want you to stop and ask yourself, was this object simply shaped by a mold, or was it shaped by motion? Thanks so much for hanging out and learning with me today. Catch you next time.